Any sufficiently large data set is going to outgrow a single computer. If that data set is maintained by a large group of people, protocols like Paxos can help them coordinate and achieve consensus on their updates. This is Data Skeptic Consensus, in the 24th installment in our series about how multi-agent systems achieve collective decision-making. There are many variants of the Paxos protocol, some of which we've covered on previous episodes this season. Today on the show, I speak with Balaji Arun about distributed systems broadly, with an emphasis on the notion of leaderless Paxos.
My name is Balaji, and I'm a PhD student in the Systems Software Research Group at Virginia Tech. I'm broadly interested in building distributed systems, and I've been doing that since my master's and my PhD degrees over the past 5 years. Broadly, I focus on building reliable and high-performance distributed systems. Very specifically, I work on this topic of consensus and agreement protocols, where I address different properties of them, such as scalability and resiliency to different faults. Previously, I've also worked on addressing the performance aspects of certain classes of consensus protocols called the Leaderless Consensus protocol, which I believe is the topic of today's discussion.
Yeah, could you maybe draw that distinction? We've talked a little bit about Paxos on some episodes, but had a very leader Paxos bias to that, I guess. What does it look like to do leaderless Paxos?
The main reason you would want a leader in a Paxos protocol is because you want agreement among a collection of processes. It could be nodes that are spread around in a wide area network, or they could be in the same local area network. And the important problem the leader solves is the type of conflicts, because if you allow anybody to propose values, then they might not reach agreement quickly in fewer communication steps, and that is critical. So that is why classically Paxos protocols have been proposed with a leader so that you can have termination in fewer communication steps. A decision can be made in, let's say, 2 communication steps. However, what differentiates a leaderless Paxos is that you remove the requirement for a leader and introduce a different mechanism so that even without a leader, these different nodes can agree on a same set of values that they agree and execute as part of their state machine.
Do we have to give anything up to go leaderless? Do we lose eventual consistency, or what's the cost of this?
Consistency-wise, we are still able to get linearizability. We don't lose anything per se, but however, the protocol itself gets more complex and more nuanced and subtle. Paxos itself is a complex protocol to understand and dissect. However, these leaderless protocol, because of more addition to the original Paxos protocol, can get more complicated.
You'd mentioned scalability as one of the interesting things to study in these consensus protocols. Most of the papers and research I did in learning these things will give me examples of quorums of 5 or 7 nodes, which of course are great, right? That's the way to learn it. But in reality, it's internet and cloud scale. Maybe we'd like to have orders of magnitude more nodes. What are some of the scalability challenges you bump into down that path?
You mean in terms of leaderless protocols or just in terms of consensus protocols?
Well, either way, maybe we can stick to your precise work, or if you think it's valuable to contrast it with a more generic case, that works too.
In terms of scalability in the crash fault tolerant space, before I get deep into crash fault tolerance, let me just specify a little bit on the fault models themselves. So typically people work in the crash fault tolerant space if they're solving consensus for a single organization use case or a data center use case where people deploy their internal databases and stuff like that. And the assumption in the crash fault tolerant space is that the machines can simply crash, but they cannot behave maliciously in the sense that when they reach agreement, they don't behave in a way as to deviate the consistency of the values that is being agreed on. This is in contrast to the Byzantine fault-tolerant agreement problem, which addresses a different set of use cases like permission blockchain applications that require much more scalability than that is required in the crash fault tolerance space. Typically, when people talk about BFT, they talk about scalability to 50 or 100 or more than 100 up to thousands of nodes. But in crash fault tolerant space, people typically talk scalability up to 5 or 7 nodes. And that is for a very specific reason. And that is that consensus protocols in general, they tend to be very expensive in coordination, and their performance tend to get much worse as you scale to higher number of nodes. And for blockchain applications, if you look at the absolute numbers, the performance of BFT protocols for blockchain applications are much lower than CFT protocols. The reason we stick to a fewer nodes in the CFT protocol is because there are other mechanisms that we use, like sharding and stuff like that, in order to achieve scalability in a data center setting.
Yeah, good point. I think often overlooked. Could you drill down a little bit on that? What does something like sharding afford us in scaling out?
What sharding brings to the picture is that, let's say when you have a database and you want to replicate it on a bunch of nodes, it is so possible that when you do a replication, you might still meet the physical limits of a given machine in terms of storage or memory. And that is when you want to introduce sharding in order to scale your application beyond what is permitted by a single machine for its storage and memory. And another advantage of sharding approach is also that you get more performance, because now rather than having one set of replicas, you have multiple different set of replicas for different shards. Now you can process more requests on each of these shards and get more performance out of them.
One of the challenges some organizations have had to face in scaling up their technology is to start thinking about geographic replication and scaling, around the world. Naturally, physics puts a sort of limit on how quickly you can communicate across the globe. So I imagine there are added challenges to having a consensus protocol when we scale up that far and know that replication lag is kind of relative to location. I know that was one of the motivations for the work. Is that the primary motivation, or is that just a major component of it?
That is one of the motivation of the work. The work itself builds off existing literature in the space. So there has been prior investigation on making these consensus protocols work well in geographical setting. And the first protocol to sort of try this approach is the Fast Paxos protocol, written by Leslie Lamport nearly a decade and a half ago. And his principal idea at that time is that the idea of Fast Paxos is basically that whenever you do not want a leader, you should avoid using the leader and bypass the leader in order to get more performance. So you can sort of imagine a geographically replicated deployment of a consensus system across continents, and the latencies between these regions can be upwards of like 100 milliseconds in terms of the round trip latencies. And you can imagine like putting a leader on one of these regions, and what would happen is every other client in every other region around the world must talk to this leader and pay for that additional geo latency of upwards of 100 milliseconds usually to get their commands committed and executed by the state machine. However, the idea really stems from what if you could use your nearby replicas rather than going far in through the ocean links to reach the remote leader. And that is sort of what Fast Paxos does. It basically says that you can send the request to the node that is closest to you, and that node will try to get agreement on that request that you're trying to submit. If it is not able to reach agreement, which can happen if multiple nodes are trying to propose client requests at the same time, then you fall back to the leader, and the leader will say who goes first and who goes second. And this is sort of a tie-breaking mechanism the leader is used for in the Fast Paxos protocol. And the motivation behind the work I did is that you want to get away with the leader permanently, because conflicts are not rare in applications. So even though you're able to solve consensus efficiently whenever there are no conflicts, there could be cases when there could be very high conflicts, and then you fall back to the leader for every single command, right? So in that case, there has been work along this line that introduces different mechanisms to remove the leader in itself. The first work to do that, I think, is ePaxos, called Egalitarian Paxos. And what that work sort of does is it sort of introduces a dependency graph mechanism. So rather than replicas depending on a leader to give them which command to execute first, second, and so on, the replicas itself communicate with each other and sort of build a graph graph that would tell them what the dependencies between these commands are. And based on these dependencies, they can execute these commands on the state machine in a deterministic way across all these different replicas. Thereby, you still get the highest possible consistency of linearizability. Moving on, what we did with Caesar was we observed some of the performance bottlenecks with existing protocols and we tried to overcome them. First of all, if you go ahead and look back at ePaxos, what it does is, with its graph mechanism, is that every node can be a coordinator for the command it receives from the clients, and it tries to propose them to a bunch of nodes and tries to reach agreement on them. And the important property to reach agreement in ePaxos is that the dependencies collected by the coordinator for a given command must be the same from not all, but a quorum of replicas in the system. And only when all these replicas observe the same dependency graph, then the command can be committed. And this may not happen in the first communication round trip. It may take another round trip for all these replicas to consistently see a same graph, because the same graph is required by the replicas to reach a deterministic commit order. Otherwise, you will lose consistency. And because of that, even if there were slightly higher contention, then ePaxos would revert to using the slow path decision, which is the decision when the dependency sets don't match, and then the coordinator has to perform another round-trip communication to sort of enforce the dependency set. And we thought this is an opportunity that we can address. And what we do in Caesar is that we sort of remove the idea of a dependency graph and replace it with notion of a predecessor. So the difference between a dependency graph and a predecessor is very simple. What the predecessor set does is that it sort of lists a set of commands that would have to be executed first before the command in question should be executed, which is different from what ePaxos did. It sort of builds a directed graph where there are links to different commands. If you imagine the nodes in the graph as different commands, then these different links can get complicated, in which case you need to bring in algorithms for graph analysis, like finding strongly connected components and so on, to sort of work on this graph, analyze it, and come up with an execution order. So by basically swapping the predecessor's dependency graph with the predecessor set, what we are able to achieve is that we don't need a graph anymore. If we don't need a graph anymore, we don't necessarily need the replicas to see the same dependency set. And that was the main reason ePaxos was taking additional communication steps, because now we don't need those two additional dependency set. We are able to reduce latencies or in scenarios that ePaxos would otherwise take additional communication steps. So that is one of the major changes. The second change we made is that because we introduced a predecessor set, this predecessor set does not give you an order by itself, because it only says execute me after you have executed a bunch of other commands. In order to come up with that execution order, we introduce a logical timestamp based mechanism, which is, you can imagine, just like a sequence number that is used even in classical Paxos and other Paxos-like protocols. So whenever a command is proposed now, you attach them with a timestamp, and that timestamp will decide when that command will be executed with respect to other commands. So how do you execute it? Whenever you have a command with timestamp, let's say, for example, 100, you now want to make sure you have executed all the commands less than 100 before you execute the command with timestamp 100. And how do you know what are all the commands that are timestamp less than 100? The predecessor set of a command will basically tell you that information. So by combining these two mechanisms, we are able to ensure that fast decisions can happen even if replicas necessarily don't agree on the dependency set. They just see different dependency set. But because they will respect this timestamp, even when there are conflicting proposals, we still can ensure that in two communication steps, most commands are decided.
I think that's a novel approach, taking advantage of the dependency set rather than having to have the whole graph. And relying on the timestamp is very intuitive as well. Do I need to now make an assumption about synchronizing clocks or a common timestamp method or something like that? Do I have any additional constraints in that regard?
No, because this is a logical clock, there is no need for synchronization. This is not reading your physical clock on the machine specifically. This is just numbers that are incremented. So the property that we provide with the timestamp is basically monotonicity. Monotonicity is that the timestamp must be incremented in some way that it's not decreasing. And it need not necessarily be sequential. Sequential means that you have to increment by one all the time. It is not possible because different nodes go at different speeds. So you need not assign sequentially increasing timestamps to these commands. So even when you don't do that, the combination of timestamp and this predecessor set will ensure that your commands are executed in the monotonically increasing order, but not necessarily with sequential timestamps.
I'd love to revisit that notion of fast versus slow decisions you were mentioning. Can you remind me the distinction between those and what advantages these fast decisions give me?
So a fast decision allows a command to be committed and executed in only two communication steps. So this is without any client interaction. So the moment a client sends a request to a node, that node would send it to a bunch of replicas in the system and then wait for responses from them. So those two communication steps, sending and receiving a quorum of responses, is what would constitute a fast decision. If you're able, at that end of that second step, if you're able to make a decision, then it is called a fast decision. However, a slow decision is when you're not able to terminate the commitment of that command at the end of those two steps. So now you need additional mechanisms. Different protocols use different mechanisms. In the case of Caesar, you need additional two communication steps and other conditions in order to make that possible.
I know this is really at the protocol level, so I'm not sure if you've thought how implementers will take advantage of this innovation, but do you have any thoughts on particular industries or problems? Will this be great for hotel reservations because they're, you're probably booking local, or maybe it's video games? What sorts of systems can benefit from the fast decisions?
This is where I might have to touch a little bit on the strong consistency versus the eventual consistency model. So in strong consistency that Paxos-like protocols provide, a request is committed and all the replicas agree on this committed value at that particular sequence in their log. However, in eventual consistency, what could happen is that the replicas can deviate in terms of the sequence of requests that they are executing, and there are other reconciliation mechanisms that allow them to converge eventually on a final state. And this sort of relaxation for eventual consistency protocols give them the performance edge. So they can go much faster, in orders of magnitude faster even than consensus protocols. So for some applications, eventual consistency is all they need. For example, shopping carts are the classical examples that people use for having eventual consistency as examples for eventual consistency protocols. But for Paxos-like protocols, people typically build consistent databases, and I'm not really aware of high performance scenarios that people use Paxos-like protocols today, because even the latencies that are provided by these fast decisions are still in orders of magnitude higher than those provided by eventual consistency protocols. So I'm not really sure what kind of applications can benefit. But applications that require strong consistency as well as low latency can really benefit from such an approach.
Well, I think the boring answer is databases, right? And then it's how one uses their database. But being able to provide services like this as a service is a huge benefit to any application developer, even if they don't know what's going on under the hood. One of the components in the paper was some actual empirical results that I don't always see in every network protocol paper. So I was glad to learn a little bit about how the theory works out in practice. Could you share some details on those experiments?
The protocol we developed is very sensitive to contention. That is because different replicas can issue conflicting commands, and the more conflicting commands they introduce into the system at the same time, the more contention there is between replicas and the more pressure is on them to form a consistent order among different replicas. And this is what we focused on in our evaluation. At very low contention, which is basically every replica that is in the system propose commands that are not conflicting with other replicas, then you sort of meet the lower bound of any consensus protocol. Like you take only few communication step, which is about 2 for a Paxos-like protocol. So in that case, Caesar's performance is not really better than the known protocols in the space. However, as we move higher along the conflict spectrum, so if more and more conflicts are introduced, that's when we observe that our Caesar protocol was able to provide better latencies, also higher throughput compared to existing techniques. And the reason for that is that mechanism that I mentioned, the timestamp-based mechanism along with the predecessor set, allows fast decisions to be taken most of the time. And I did not talk about this, but there is also another mechanism called wait condition in the paper that sort of allows replicas to not reject certain timestamps and force the coordinator to take the slow path. That is also one of the mechanisms that helps in reducing the latency. So all these three mechanisms literally help Caesar keep the lowest possible latency for about very low to about medium contention scenarios. So what I mean by contention is that the probability of any two replicas proposing commands at the same time that conflict with each other. So if there is a 50% probability, then Caesar performs better than other protocols. Otherwise, if the probability goes higher, then Caesar performs the same as other protocols, but lower than 50 and more than 0, then Caesar can perform better than other protocols. So the sweet spot for Caesar is in this low to medium conflict scenarios, not 0 and not 100, basically.
And what do you see as some of the next steps? Where does Caesar, or perhaps if this is, the most value you can get out of the predecessor set insight, maybe there's other paths you're on. What comes next for you?
So follow-up of the Caesar work, we did another follow-up work that sort of inspired from the performance evaluation that we observed here. So as I mentioned, the sweet spot of Caesar was between this low and high contention scenarios, not when your contention is 0 or not when it's 100. And we noticed that for these 0% contention and for these higher contention, there were other protocols already in literature that served that purpose. For example, at 0%, there were protocols such as Paxos or M2 Paxos that served very well at under 0%, that performed better than Caesar and many other protocols. But for 100%, we observed that most of the time you are better off with using a classical multi-Paxos protocol, which is leader-based. And with this intuition in mind, what we developed is sort of a consensus framework that would allow you to switch between consensus protocols at runtime in response to the contention that it sees in the system. So for when the contention is very low, the framework would switch to using an ePaxos-like consensus protocol. As the contention increases, the framework would observe it and adapt by making the switch to a Caesar-like consensus protocol, and so on and so forth. Like as the contention lowers, it also would switch back to a protocol that can provide the best performance for that contention level. That is one follow-up work that we did post-Caesar.
And is that framework more theoretical, or is that a software implementation?
That was more of a software implementation.
I'd love to unpack that a little bit and learn more about it. I've never encountered a sort of generic open, I don't know how open you guys have chosen to make it so far, but a protocol or whatever where different researchers or even industry groups could kind of collaborate on common interfaces. Is that what you're going for?
What we built is just sort of a framework that is more suited for Paxos-like protocols. So thing about Paxos-like protocols is that they share some of the interfaces, like the propose and the decide interfaces, the way you would get a command into the system and then also wait for a decision from the system. They are fairly consistent for many Paxos-like protocols. However, the internal details of each of these protocols differ significantly. One of the biggest challenges we had while developing this framework was that the underlying data structures were all different, and we could not find a way to represent these different data structures under a common framework. So we had to develop different data structures, different mechanisms to write the logs to the disk for each one of these protocols separately. In that sense, we were not able to achieve a mechanism to construct protocols on top of a common framework, but rather we were only able to achieve the performance gain by putting these different protocols together within a common framework.
Sounds good. Well, tell me what's next for you.
Currently, what I'm working on is more related to the scalability aspects of consensus protocols. And right now, I'm working on Byzantine fault tolerance consensus protocols. The way I'm looking at this problem is not just at Byzantine fault tolerance protocols, but at the intersection of both crash fault tolerance and the Byzantine fault tolerance. Because I have experience with crash fault tolerant protocols and able to see some of the design decisions in Byzantine fault tolerant protocols differently than a person with a pure BFT mindset would see it. So in that regard, what I'm trying to do is sort of use different mechanisms like trusted computing base. And what a trusted computing base is that it is a part of your process that you can trust, especially in Byzantine fault tolerance, where you don't trust replicas, some of the replicas on a subset of nodes that are part of your system. What this trusted computing base allows you to do is that rather than trusting the whole system completely or not trusting part of the system completely, it allows you to trust part of a process among all the processes in the system. So one example of this is the Intel processors with SGX capabilities. What SGX is called is secure guard extensions, which is a capability of a processor to execute code that does not interfere from malicious behavior of, let's say, an operating system or any other software stack. And I'm trying to use this particular hardware capability as a way to reduce the complexity of Byzantine fault tolerance protocols by making them resource efficient in terms of the number of protocol steps that are required, by making them more close to the CFT model by leveraging this trusted protocol is what I'm doing right now.
Well, exciting stuff. I look forward to following that line of research as well.
Thank you.
Well, Balaji, thank you so much for taking the time to come on the show and share your experience and expertise.
Thank you so much. Thank you for your time.
That concludes this installment of Data Skeptic Consensus. Our guest this week was Balaji Arun. Claudia Armbruster is our associate producer, Vanessa Burciaga does guest coordination, and I've been your host, Kyle Polich.